So next we're going to hear about symmetry breaking in the subgraph isomorphism problem by Joe. Please.
Hello everyone. For the last 6 or so months I've been working on success symmetry breaking in the subgraph isomorphism problem, and in particular implementing that in the Glasgow subgraph solver with varying degree of success. So I'll start with some initial definitions. So graph isomorphism, as you may have heard a few days ago, if I have two graphs G and H, they are isomorphic if there is a bijection between the vertex sets that preserves adjacency. So I can move around the vertices of this one to make it look like this. Subgraph isomorphism is very similar to that. The question consists mostly of, can I find a copy of this graph in my bigger graph? And we call the small graph a pattern and the bigger graph a target. Sometimes that goes by different names, but I always use these. So this is the decision version of the problem. After looking at that for a few moments, you may notice that yes, we can find a copy of that, as you can see. In fact, some of you may notice that we actually find several copies of that, but I'll get onto that in a minute. Yeah, so another question is, how many copies can we find? So in this graph here, you can see that there are several different copies here, although maybe slightly more than you would expect on first look. So a quick break after that. Those few very fast definitions. Is this graph planar? It's not too easy for a human to work that out. If you know the trick that I'm about to use, then that'll maybe give you an indication of whether it's planar or not. But after just a couple more moments, we can see that using subgraph isomorphism, we actually have a K33 bipartite graph. So by Kuratowski's theorem, that is not a planar graph. There is no way we can draw that without the edges overlapping at least once. And that's a cute little application of subgraph isomorphism you can do. And it's pretty easy for the solver to do this particular example, but for a human, as I'm sure you found out, it's not that easy. So, as I said before, in this example, which is a very basic example, we actually find 6 solutions here, even though only really the first one that we find is interesting, and the rest of it really is wasted work. So you have A to 2, B to 3, C to 4, and then 2, 4, 3, 3, 2, 4. It's all really the same solution, just in a different order. And our search tree looks very similar for a lot of it, and that is a waste of time, really. So an isomorphism of a graph onto itself is called an automorphism, and the set of all automorphisms of a graph is called the automorphism group. That will become useful very shortly. This lemma here is a handy one, which says if there is an automorphism mapping the pattern vertex P1 to a pattern vertex P2, and the solution exists that maps P1 to a target vertex T, then an equivalent or symmetric solution exists for P2 mapped to T. And the proof of that lemma follows directly from composition of isomorphisms are isomorphisms. And also just another definition here, the set of all vertices P1 to Pj such that P maps to all Pi under automorphism is called the orbit of P, which is denoted all P one at a time. Yeah.
What do you mean P maps to? So what does it mean P maps to all Pi? Sorry, I missed the.
So under automorphism, if I have an automorphism which maps a pattern vertex P.
And this automorphism is P, right?
Yeah. Sorry.
No, the automorphism. So okay, this is the orbit here. So there exists some automorphism that maps P to okay.
Yeah. Hopefully I'll illustrate it a little bit better with this example, because that was a bit of a mouthful. I accept. So we say we have this automorphism here phi, between these two very subtly different graphs, which is just swapping the labels of A and B. And I also have this solution that we found before, which is A to 2, B to 3, C to 4. Then by the lemma, we must also have an equivalent solution which maps, because phi of A is B, so we must also have a solution where B maps to 2. And as we can see, yes, we do have that solution just here. B to 2, A to 3, and C to 4, as we were expecting. So that's pretty handy when we're trying to break symmetry. So if we compute all of the pattern symmetries, the variable symmetries, we can see that we have, in this graph, the automorphism group is S3, which is of size 6, but we actually only need these 3 constraints to break all of these, because I can swap these labels, I can swap these labels, I can swap these labels. And so we say A is less than B, A is less than C, and B is less than C. And that is sufficient. That's sufficient. So just to explain what I mean by A is less than B. The value assigned to variable A must be less than the value assigned to variable B. I will go into a little bit later what it means to be less than a value in this context. So now if we look at the problem that we saw before with all of these 6 solutions, we can see that 5 out of these 6, sort of as we were expecting, are knocked out by our symmetry breaking constraints, which means we don't waste quite so much work finding these symmetrical solutions, but we do still get 1. If we had knocked out all of them, that would be very bad news, because we've gone from sat to unsat, which is wrong. And we can do a similar thing for value symmetries. So there is another lemma here, which is very, very similar to the first lemma. If there exists an automorphism which maps target vertex T1 to target vertex T2, and a solution mapping P to T1, then an equivalent solution exists mapping P to T2 instead. I haven't provided an example of that. Okay, so looking at our target graph, we can see that in fact there are only 2 elements in the automorphism group, just this way and this way. And so we can identify which representative of the automorphism group we want with one of these 2 constraints. And it must be only one of them. And I'll go into that in a little bit. So just for some more context, what does the target constraint 5 occurs less than 3 mean? So we call this occurs less than in this context because it's slightly different. What it means is if the value 3 is assigned to a variable, the value 5 must be assigned to a smaller variable. That's all.
So I should think of pattern vertices as variables and the values are the target graph vertices?
Yes, yeah, exactly, yeah. So we're allowed to say silly looking things like 5 is less than 3 because 5 occurs less than 3, because really the fact that I've chosen numbers for the labels is entirely arbitrary. I could have those in any order, so I'm allowed to have a partial ordering on my value labels. Yeah. So if we now look, if we've taken 2 as less than 4 in this case, using 2 occurs less than 4, using that target constraint, we can see that we identify these 3 solutions and then don't count any of these value symmetric solutions. If we had used both pattern and target constraints, we would still just get 1 of the 6, which gets annoying when we're trying to retrieve the original count when we've broken both symmetries. That's a problem that I'm currently grappling with. So as you may have noticed, subgraph isomorphism is non-surjective on the target graph. So we don't have to pick all of the values. So target constraints picked at random at the top of search might be ignored. We might pick badly. If we had picked 0 less than 1 in that case, you see here, these two, they're not part of the solution, so we wouldn't filter any of those solutions out, which is unfortunate but unavoidable. So this is roughly the, I should mention actually at this point, if we had picked both 0, 1 and 2, 4, we run into some problems because I can always produce a relabeling of this graph that will break if I pick both 2, 4 and 0, 1. I can switch these labels and not these labels, and then the automorphism between the isomorphism between those will be labeled as unsatisfiable, even though it's obviously not. So we can only pick at most 1 from each generator. So the process for generating those constraints is not immediately intuitive, but here's a rough outline of the algorithm. So first of all, we compute the generators for the automorphism group, which is a permutation group. And then for each generator, we pick a base point to stabilize one of the vertices. We record its orbit, which is, as you recall, everywhere that it could be mapped to under automorphism. We check which points still permute without moving this base point. And then we repeat steps A and B until the whole graph is stable under this generator. And for all non-trivial base points, B1 to beta 1 to beta n, we add symmetry constraints. Beta I is less than gamma for every gamma in the orbit of beta I. So this is what it looks like when we do that, when we follow this process. So if we have our pattern graph here, A, B, and C, first of all, arbitrarily we pick beta 1 as A, and so we stabilize the vertex A, so we're not allowed to move that anymore. And we find that A could have been mapped to A, B, or C, because the identity mapping is an automorphism as well. And so we say A is less than B and A is less than C. We then find that once A is stable, we can still permute these two vertices. And so we also say, given that A is stable, B is less than C. And now given that A is stable and given that B is stable, C can't go anywhere. And so we can just ignore that basically. Doing that at the top of search might waste effort. So as you can see in this example, the solver is clever. It does some clever inferences. The solver would never bother checking these leaf nodes here because it knows that because of the vertex degree, none of these pattern vertices could map to a leaf node. However, using the symmetry breaker at the top of search, we could get a lot of symmetry breaking constraints for this that are not useful at all, that do not reduce the search tree. But propagating those constraints takes time. Currently, it takes quite a lot of time. So we would prefer to avoid generating useless constraints. So how do we do that? So fixed order symmetry breaking, which is what I've talked about so far, picks a base at random before search. It might be unlucky. It might choose things which are never part of the solution and don't save us any time. If we could construct the base during search, adding constraints as we go, that would be much better. It would guarantee that at least we're hitting the constraints that we use in the search tree at some point, even if it's not all that useful. If we just hit them once and then never touch them again, that's still at least once that we've used it. So the process for that is every time we encounter a vertex which is not already in the base, we add it to the base, generate the constraints, add that to the list, and propagate those from then on. The smallest element in each pair is just the element that we encounter first in the search tree. So suppose we've got this variable constraint A is less than B, and the value constraint 4 is less than 2. We can find a solution in this arbitrary case that A maps to 4 and B maps to 2. We want to accept that solution. So we have to be a little bit concerned with how we propagate these constraints, what they mean to the solver. So by constructing a flexible value ordering from the value constraints, so we started off with just the natural ordering, and then we move 4 in front of 2. We can avoid accidentally adding conflicting variable value constraint pairs, which might take us from sat to unsat, which is bad news. So experiments. I have run some admittedly fairly naive experiments using this data set here, which consists of a collation of interesting graph cases. So some of them are randomly generated Shreddy graphs. Some of them are from biochemical reactions, medical imaging, scale-free graphs. Lots of varied cases. Some of them are very hard, some of them are very easy. And I've recorded various things. That stuff that I'm going to show you now is the runtime, which I'm most concerned with. So here we go with the fixed ordering results. So this is my x equals y line. You can see there's quite a lot of cases which are sort of stuck to this line. These are the cases where my automorphism group for the graphs is maybe just a C2, or there is no symmetry at all in the graphs. And in that case, with the very slight overhead from checking that we don't have any additional constraints, and so we don't speed up and we don't slow down. This, I should add, is run with a 5-minute timeout. So everything along here is where the solver with no symmetry breaking is timed out, and the solver with symmetry breaking has produced a solution. And everything along the top there is where the solver would have solved it, but the symmetry breaking has timed it out. So everything down here in this corner is very good news. It means we've got a big speed up. Everything in that corner is pretty bad news, because in particular, right in the corner, the solver was doing that in no time at all and is now taking 5 minutes to not give me a solution, which is not great. And you can see a lot of the cases are clustered around the origin here. When we do it with flexible ordering, only adding constraints when we need them, you can see it's a lot better. It's mostly it executes very quickly. There's a lot of clustering around here, which is where the solver is timed out, and we've got much faster. And then less cases, still a few, but less cases up at the top where we've timed out when we hadn't done previously.
And so what you're doing is enumerating all isomorphisms in the one case and all the ones that are not broken in the other case, or do you stop after finding one? So what's the
this is for enumeration. Both times we're counting all of the solutions.
But you're not doing the counting yet when you do the symmetry breaking, because you don't know how to reconstruct it completely, didn't you say so? Or
yes,
or
so
you only do symmetries where you do know how to.
No, sorry. This is counting the this is counting the asymmetric solutions. I haven't added the step to go back to the original count.
But there might be symmetric solutions still in there, or not? Do you have a guarantee of complete breaking? Or
no, we can't guarantee completeness.
okay, so all the non-broken, counting the non-broken solutions versus counting all solutions is what we're comparing.
Yes.
Okay.
Yeah. So I've got some data here. This again is very naive, please take the numbers with a degree of skepticism, because this in particular, these are just the ratio of runtime between with symmetry breaking and without. I have a threshold here, which is just to avoid this cluster around the origin, which gives me near meaningless results when I've got one executing in 1 millisecond and one executing in 10 milliseconds. So as we increase the threshold, and we're looking just on this side of the axis, we can see that we get a lot better when it's, in particular, after about 5 seconds for flexible ordering, and after 15-20 seconds for fixed ordering. We can see that we're starting to see a speed up, whereas in the cases which execute very, very quickly, we're slowing it down slightly. We also have just a count of the solutions which are solved with symmetry breaking and versus not solved. So we can see that with flexible ordering, we only have 10 solutions where we now time out, but we didn't previously, whereas it's 94 for fixed ordering. So that is quite a bit better.
Does this include the symmetry detection time?
Yeah, this is from input to output.
Which explains maybe why on very slow instances you're losing a lot.
Yes, yeah.
So,
And then on this next slide, I have just that separated into unsatisfiable and satisfiable cases. So as you can see, we're much better at satisfiable cases. I'm not 100% sure why that is. I suspect we're putting out more of the search tree. And you can see on unsat cases we're only better after sort of 10 seconds, 20 seconds in the flexible ordering case, and it takes much longer for the fixed ordering to be better in unsatisfiable cases. So any questions? No?
Wouldn't you expect it to be faster in the satisfiable cases? Because if you have symmetries and you're enumerating all of the solutions, then
Yeah.
you are not enumerating all of the solutions, so it must be faster.
but if in the unsatisfiable case, you're searching through your whole search space, and now you're not doing that.
Yeah,
There are no solutions. I mean,
but I think usually in start why it's faster is because you stop once you have the first, right? And this does not apply if you you are forced to go through the entire tree in any case. Right?
I'm not surprised by this distribution, but
But is it still faster in the unsatisfiable case? I don't really.
yeah, it should be. It's just I haven't included the later.
How much overhead is for the symmetry detection?
So detecting the symmetries is nearly inconsequential. Propagating the symmetry constraints is currently what takes up most of the time.
That's my fault.
The obvious question is, what would it mean to have proof logging for this?
That's an excellent question.
That's a tough one.
well, I think this should work with dominance, no? The constraints you're deriving.
No, but in our enumerating.
Proof logging for enumerating, yes. That's the same as with the SMS. Well, I mean, you don't need to worry about the complete breaking because it's not happening. So that's already.
No, but I think so the way I understand it, the goal is to recover the original count, right? Yeah. Or is it not? Yeah, because recovering the original count is like it's graph isomorphism completion, basically. And
so then the first question is how to do it and not how to proof log it.
Yes,
First,
I think.
yeah.
Other questions? So then let's thank Joe again.